Hi, we'll be looking at the Model Predictive Control and its applications. We'll be seeing the finite horizon MPC, dual mode MPC, constrained optimization. In the last lecture, we have seen about unconstrained optimization. Now we move on to constrained optimization, how to deal with the quadratic programming, the algorithms that deal with the quadratic programming, examples, recommended reading, and summarize. This is the effect. Before going into the programming part or the algorithm, we will see few features of MPC. The effect of horizon length. Like when we are driving a car, the more that we look forward, the more control we have over the car. So if you can see only a few meters, say due to fog or so, then we will have less control. If a sudden turn comes, we may not be able to handle the car properly, drive the car properly. But when we can see for a long distance, then when the turn comes, we can take action appropriately beforehand. So MPC is also like that. As we can see, as the horizon length is more and more, we can take more appropriate action before if there is any set point change, or it can handle, we have a better control over MPC. So a longer horizon is needed, especially for non-minimum phase systems. The speciality of non-minimum phase system is that they will have zeros at the right half of a spline, and it will be difficult to control such a system. And they have a phenomenon like the initial response will be in the opposite direction to the actual response. So if the horizon is very small, then what will happen is it will misunderstand the direction. So we can handle the system better, especially a non-minimum phase system, if we have a longer horizon. So thus the concept of infinite horizon MPC came up. So we will be optimizing the cost for an infinite number of horizon. But the problem is that as the number of horizon increases, the computation requirement also increases. So practically we cannot implement such a infinite horizon MPC. So that thus this gave rise to dual mode MPC concept. In dual mode MPC, we will be considering a cost up till n instant, and in order to accommodate the cost after n until infinity, we will add another cost in the it is called the terminal cost in the optimization problem. So here we will be optimizing the variables until n terms, 0 to n minus 1 terms, and then we will take the state feedback control after that. So we'll just multiply with the states after this n instances. So this is mode 1, and the second one is mode 2. So in the mode 2, we are assuming that we will be sufficiently near to the optimal point or set point, so that no constraints will be activated. So the constraints will be active only in this instances. So we will be requiring to run the MPC only in this instances. And after that, we are assuming that the states are near the set point, and so no constraints will be active, and we just need to carry out the state feedback control, so like LQR control. So we will not be running any optimization problem here. So that is a dual mode MPC concept. Now this is what I mentioned earlier, a terminal cost. To evaluate the infinite horizon cost over a finite horizon, we add a terminal weighting matrix. So for the terminal state k plus nth state, given we are at the kth instant, we will predict the k plus nth instant and we will multiply with the terminal cost q bar, and this terminal cost will be added in the optimization cost. It will account for the cost beyond n until infinity. So we will discuss how we are calculating the terminal cost in the later slides. So this the function of this terminal cost is that we will, in dual mode MPC, we will consider it to account for the cost beyond n until infinity. So now before we will slowly begin with the quadratic programming problem. So before that, we will see what is an optimization problem. We will brush up the basics of optimization problem. What we are doing is we are either minimizing or maximizing a function and the terms of a function. So z is f of z, we are trying to minimize or maximize. So we will, z are the different variables that we are trying to minimize or maximize. Subjected to z belongs to S, where S is a set of feasible domain. The feasible domain is, suppose they have some constraints in this. So we cannot consider the entire space for optimization. We will consider certain feasible space based on the constraints where we have to find a solution. And z are the decision variables. So we will be adjusting this different values, substituting this different values of z to minimize or maximize this function. So z is the optimization problem domain, the total optimization problem domain, and S is a subset of z, which is a feasible domain. So the optimal value is represented as f star, which is nothing but the value of the function when we substitute the optimal z. So which will always be less than, this optimal value will be less than for any z in that domain, in that feasible region. So any point in that feasible region, when we substitute, we will get f of z, and our optimal point will always be lesser than any other point in the feasible set. So a problem is said to be infeasible if the set S is empty. So, and the problem is said to be unconstrained if the set S is equal to Z. So the optimal problem domain is equal to the feasible domain, then it is unconstrained optimization problem. Now we will discuss a convexity. This is the basic test for a convexity. If lambda is a value which lies between 0 and 1, and we consider 2 points z1 and z2 in the domain S. So if this equation is satisfied, if lambda z1 plus 1 minus lambda z2 belongs to S, then we can say that the set S is a convex. Set S is convex for all z1 and z2, for any point in z1 and z2. If this equation is satisfied, then S is a convex set. The fundamental property of convex optimization problem is that it has a unique global optimal point. So in nonlinear optimization, we may have different optimal points, but here we have a unique global optimal point for a convex set. That makes the problem easier. So we will begin with convex optimization problem, and then we will discuss about non-convex optimization problem as well towards the end of the lecture. Now the optimality conditions. For a function to be minimum or maximum, we will take the derivative of that and equate it to 0. At the minimal point or the maximal point, it will be, the derivative of that function will be 0. The same concept is used here. For a convex unconstrained optimization problem with a smooth cost function, the gradient vanishes at the optimization. So the gradient, when we take the gradient, it will be equal to 0. Z is a global optimizer if and only if delta Z equal to 0. So when we take the gradient, it will be equal to 0 at, and that those points of Z are the global minimizer or optimizer, global optimizer. So Lagrange duality theory. So these are the concepts which will be seeing both Lagrange duality theory and Karush-Kuhn-Tucker conditions. These are the conditions that needs to be satisfied for optimization problem, a constrained optimization problem to be minimum. So we will see what a primal problem is. Primal problem is nothing but what we have seen earlier. Like we will be minimizing or maximizing the function, and we will find those points which will maximize or minimize this function. So Z subjected to that feasible domain. This is inequality constraints and this is equality constraints, and F star is the optimal value. So we have M inequality constraints and P equality constraints. So we are optimizing this problem subjected to these constraints. So that is a primal problem. And the dual problem is we will augment the objective function with the weighted sum of constraints. So this is the objective function, and we will augment it with the constraints with some multiplying with some variables. So that variables are called dual variables or Lagrange variables. So these functions, as we will be using different values to multiply it with the constraints. So what is Lagrange duality theory says? Duality cost, we will say we will try to maximize Z with this cost function L Z U V. So this is nothing but the Lagrange dual function. We are trying to minimize this Lagrange dual function with respect to Z. So this is a function which has three different variables to consider, and we will, this dual cost is nothing but it is only in terms of U and V, and we are trying to minimize this cost. This will be unique with in terms of Z, and will be variable different values can be substituted for U and V. So what is Lagrange dual problem? We will find the supremum of UV in the dual cost. So that results in the an equivalent problem to this primal problem. It will be equal to what we are doing in the primal, considering the optimization of a cost, considering the cost and constraints. So now why we are using the Lagrange duality theory? The Lagrange dual problem is convex optimization problem, even if the original primal problem is non-convex. So the original primal problem may not be convex. So, but we can, when we find the dual problem, it will be convex. So that makes the problem easier to solve, the dual problem, than the primal problem. Now we will see how the algorithms are implemented in Lagrange dual theory. The optimization algorithm iteratively solves a primal and dual problem and generate a sequence of primal dual feasible points, ZK, UK, VK set, until a certain threshold is reached. So the threshold is epsilon. So we will iteratively solve this condition. When this condition is satisfied, we will terminate the algorithm. So we will substitute different values of ZK and UK, VK. So primal function and dual function will be primal cost and dual cost. We will substitute different values, and then we will find the difference. If it is below a threshold point, we'll stop the algorithm. So that is how the optimization algorithms are iteratively solved to find the optimal feasible points. And these are Karush-Kuhn-Tucker conditions, which will be used to find the optimality conditions while implementing the algorithm. So these are the optimality conditions that should be satisfied for a constrained optimal problem. So the cost function and the constraints are differentiable. Now we will have the gradient vanishing at the optimizer. That is the first condition. Any primal dual optimal pair should satisfy the following conditions for that points to be optimal. So Z star is the primal optimal point, U star V star is a dual optimal point. The condition 11 is nothing but the dual feasibility condition, and the conditions 12 and 13 are primal feasibility conditions. So we will not be going deep into this, but these are the conditions that needs to be satisfied for a optimal point, the constraint optimization problem. Now we will move on to the quadratic programming. The primary advantage of MPC is the incorporating of constraints. So we will see how MPC is being implemented, how it is helpful in handling the constraints. We'll see that in the next video.